Okay, so we started talking towards the end about solids and getting into solids as we moved away a little bit from talking about liquids and some of the characteristics of liquids, including, again, phase changes, phase diagrams last time. Remember that a phase diagram is basically a graph of both the pressure and the temperature, and it basically has all the three different phases, the solid, the liquid, the gas in it, and also the transitions that occur between those guys. And you can use something like we did last time, like a phase diagram, to figure out, for example, in a combination of a certain pressure and temperature, what state you might expect to find a substance in. You could also use it as well, like we sort of did, to figure out, if you want to kind of force something into, say, the liquid state or something like that, you can figure out what sort of pressure combination that you would have to do that. So, for example, the dry ice that we looked at, again, as we know, it normally goes just directly from solid to gas under normal conditions. And we saw that you had to pretty much put a pretty high pressure in there to sort of force the carbon dioxide into the liquid state. And it was something, I think, just off the top of my head, I think maybe 5 times normal pressure or something like that to sort of force it to get into that liquid state. And again, that's why something like dry ice under normal conditions, we don't necessarily see it go into the liquid state. It goes directly from the solid to the gas. And again, when you're looking at that, as we talked about, essentially it's kind of normal conditions. So if it asks something about normal boiling points, normal freezing points, again, that's sort of 1 atmosphere is your normal sort of pressure for something like that. In terms of temperature, 25 degrees is also kind of your normal sort of temperature and stuff like that. Then we got into the solids here at the end, and we're just kind of finish up here talking in this chapter about solids and a couple of aspects of solids. We're going to really focus in on sort of crystal lattices or crystalline type structures. And again, those are the solids that have pretty good long range sort of order and very long range sort of repeatable sort of patterns of how they can sort of come together. And they do sort of form what's sometimes referred to as a crystal lattice. And they will, as we sort of talked about at the end as well, try to arrange themselves in such a way that, again, they do maximize those attractive forces, as we talked about. Again, that's the positive, negative side of everybody sort of coming together, while minimizing the repulsion forces, which is where we get areas where we have positive charges near each other, negative charges near each other. But as we also talked about, no matter what you do, you are going to get areas where you will be sort of forced, if you will, to have that sort of happen, positive guys near positive guys and negative guys near negative guys. But usually in the liquid and even in the solid sort of phase, they will try to kind of adjust themselves in such a way that they could kind of live with it, if you will, because they really have maximized that attractive forces. And when they do that, and when they sort of move around and sort of get themselves in that sort of optimal position, they will typically minimize their energy. And in chemistry, as we've talked about, essentially lower energy is good. So things like to be in sort of the lowest state of energy is sort of the most stable sort of aspect of it. And when they do sort of arrange themselves in this way to minimize energy and so forth, we get this sort of crystalline solid that has this very repeatable type patterns. And the smallest unit of a sort of crystalline pattern is what is referred to as a unit cell. I think that's what that says there. On my screen, it's kind of hard to see, but that's a unit cell. And a unit cell, again, is really the smallest part of the solid that really shows the repeatable pattern of it. And it's like a little sort of, if you want to think about square that you could kind of grab out, or a little portion of the three-dimensional structure that you could grab out. And if you sort of pick the unit cell correctly, you can really recreate the entire structure. So for example, if we had some guys that came together, and this sort of pattern. And you may say, well, it seems logical that, hey, I will just grab this guy here as like my unit cell and go, cool, I got like the whole atom going on. And that's good that you got the whole atom going on there, but we have really no information when we take this as, say, our unit cell about how it's connected to everybody else. We don't know if we should place like the next guy here, you know, should the next guy go like right above him, should it go to the right, and so forth. So although it may seem logical to grab out like the entire atom, when we go to grab, say, a unit cell out of a three-dimensional sort of structure, what we're looking for is some information about everybody else that's there. So instead of, say, grabbing the whole atom, if we did something like this and grab some pieces of several atoms in that three-dimensional structure, we will end up, if we pull out that unit cell, of something that looks something like this. And we got a piece of everybody around. And now when we kind of rebuild this, we know, okay, if we just kind of line up the square next to me, we got this guy. We put one on the square up on top. We get a little bit of this. And maybe stack another square over here. And now before you know it, as you can kind of see here, my really badly drawn here, but we now are recreating the entire sort of three-dimensional structure. Again, because when we grabbed sort of the unit cell, it had information about its neighbors, and that allows you to sort of rebuild the entire three-dimensional structure. Again, if we just grab the whole atom by itself, we have really no information about sort of how it's attached, you know, where's the next sort of circle supposed to go, and you can't really rebuild the entire structure. And you can see by just taking that little unit cell, we're able to really recreate, as I just did there, that whole three-dimensional structure. We could just continue on and we would continue to rebuild it. So unit cells are three-dimensional, usually contain 2 or 3 sort of layers of particles. Again, different layers, when you put it back together, are going to give you that entire sort of 3D structure. And unit cells are repeated over and over to give you sort of the crystal structure of that solid. And again, the important part about it is to make sure that you do grab something that has information about the neighbors. So if you look at this particular one here, we have a lot of information. We have information about 4 other atoms in that structure and a whole atom that happens to be right there in the center. So again, if we just kind of rebuild it, you can get that whole structure going on. Okay, give me a second here. Okay, so hopefully that's better, I hope. So when we want to grab these unit cells, we're looking for those really information about everybody else that's present, and you allow you to rebuild the entire, again, three-dimensional structure of it. There's many different types of unit cells. There's cubic, tetragonal, all these kind of guys here. And we're really just going to focus in on pretty much just cubic unit cells. They're pretty simple here. They're the simplest of all of them in terms of the math aspect of it. So we'll focus in on the cubic unit cells. And there's a few different types of cubic unit cells. So the number of particles in each one is that comes in contact with each other. That's what's referred to as a coordination number. And the higher the coordination number, that means there's more interaction that's happening. Everybody's kind of attracted together. There's a stronger sort of force that's attracted together. All kinds of noise today. There you go. And when they do come together in these sort of different layers, they're looking for sort of really the highest volume of coming together and packing together. And that's what sometimes referred to as packing efficiency. That's the efficiency at which all these layers can kind of come together and really pack down into really a tight, solid form, which is why when we look at solids, right, we think of them as being rigid, you know, hard to change their shape. So let's talk about cubic unit cells. The nice thing about cubic unit cells is they're all basically 90 degrees between them. And when we do look at a cubic unit cell, at the corner of each of the cells, so this is a cube, so at the corner of each of the cells, it's about 1/8 of an atom is there. So if we got an atom at the corners of the cell, we have 1/8 of an atom. If we have an atom that gets cut right down this face of a unit cell, that is a half an atom, and a particle on the edge is basically 1/4 of an atom. The nice thing about this is since they are all cubes, if we want to figure out the volume of it, we basically take the length cubed. So that's an important formula really for all the ones we'll deal with. The volume of it is equal to the length cubed. And let's take a look at some of these different ones. We'll look at each of them sort of individually here as we go through it. But these are the three sort of unit cells that we'll come across the most here. And we have the simple cubic, which is sometimes just SC. And basically, the important part here, as we'll see, is it has one atom per unit cell. So that's a really important number to know. And basically, it has an edge length of 2r. So that's an important part, 2 times the radius for the edge length. So those are the two important things for a simple cubic cell. A body-centered cubic cell, which is sometimes shorted BCC for body-centered. The difference here is, as we'll talk about in a second, it has 2 unit cells. And the edge length is 4 times r, the radius divided by the square root of 3. And the last type of cubic cell we'll deal with is face-centered cubic. So face-centered, it has actually, as you can see, 4 atoms involved. And it has a radius of, I'll put the r in front, 2r square root of 2 in terms of how the edge length is calculated. So those are sort of the important numbers. We're going to go through each of these in just here a second so that you can sort of see it. So let's take a look at these. So we'll start with the cubic cell, the simple cubic. And basically in a cubic cell, it has, as you can see here, an atom at each of the corners. And each of these atoms are 1/4 of an atom, gets cut off at these corners. So 1, 2, 3, 4. I'm sorry, 1/8 of a corner. So each of these are 1/8 of an atom. So 1, 2, 3, 4, 5, 6, 7, and 8 corners gives you 1 whole atom. So when you pull out a simple cubic unit cell, you basically have 1 entire atom. Coordination number is 6. So again, it basically will connect in 6 sort of locations. So that is a lot of connections that will happen. And that radius, or the edge length, is 2 times the radius here. And again, that number will be important in a little bit here when we talk about doing some calculations. And here's maybe a better one. You could kind of see 1/8 of an atom in the wedges here at each of the corners. And again, when you add them all together, you get your 1 whole atom. Here's again sort of like planes going through each of these circles. And again, it sort of slices off 1/8 of an atom in each of those guys. Again, obviously, when you would put all these back together, you could rebuild this entire sort of 3-dimensional structure. Here's a much better picture. Now, the next one is body-centered. So body-centered has the 1/8 of an atom in each of the corners, just like the last one. So again, we have our 8 atoms here. Our 1/8 of an atom in 8 of the corners. That gives us 1 whole atom. And we have an entire intact atom sitting right dead center of the square, basically. and that gives us our second atom, and that is how we get to 2 total atoms for this type of guy. When we calculate our edge length, it's 4 times r divided by the square root of 3. And again, that's going to be important to calculating the volume in these type of calculations. And the last one, actually, here's a better one here. Again, you can see 1/8 of the cell or the atom in each of the corners. You can see the entire atom sitting right here in the middle, kind of wedged right there in the middle of that square. And again, when you put it back together, you can see that center atom gets placed, you know, obviously back into the right spot. And the last one that you have to worry about is face-centered cubic. And again, here we have our 1/8 of an atom on each of the corners, which is going to give us our 1 whole atom. So there's our 1 atom from there. And now what we have is 1, 2, 3, 4, 5, and 6 atoms. These are 6 atoms that are on the face of the square, basically, which is why it's called face-centered. And when you're on the face, you get sliced pretty much right in half. So you basically have a half an atom for all these pink guys. And that gives us a half an atom times 6 is 3 more atoms. And that's how we get to 4 total atoms for this particular type of unit cell. Again, 1 atom from the corners and basically 3 other atoms that have basically been sliced right in half on the face of each of these squares. Coordination number is 12. As you can see, it has the highest coordination number because it's got the most atoms. So when they come together, there's a lot more contact that occurs, obviously, between them. And that important part here is our 2r square root of 2 in terms of our edge length. And here you go. Here's a better picture of the sort of the slicing that occurs. You can see that guy's, again, sitting on the face of it. So it gets sliced right in half. And again, you have 6 faces on it, which gives you 3 total atoms. So let's talk about sort of common problems that involve this. And it's something like calculating the density, for example. So we want to calculate the density here of a face-centered aluminum guy that crystallizes. So there's a couple of important information that's given to you here in this problem. And really the first one is that it is face-centered, right? So face-centered, as we just saw, FCC, means that it has 4 atoms in that guy, right? Because it's face-centered. So that's the important part of that. The other important part is the edge length formula for that one. Because it is face-centered, that was the last one that we just saw, which is 2 times the radius, the square root of 2, basically. So what we're looking for here is the density, and density is grams per cubic centimeter. So this is going to help us get to where we want to go by using that information. We ultimately need to figure out how many grams we got going on, and we need to figure out the volume in cubic centimeters. Remember that the volume of this kind of cubic unit cell is the length cubed. So we could use this formula to help us get to the volume aspect of it. So let's start with the grams part of it. And the grams part of it is going to be a calculation that we have done before, and that is using the 4 atoms to start with. So if we use our 4 atoms to start with, when you see atoms, and we eventually want to get to grams here, so we're going to do the calculation to get to grams. When you have atoms, our good friend Avogadro from way back when, right, is what we want to use. So if we use Avogadro's number, 6.022 times 10 to the 23 atoms per mole of aluminum, that will get us 2 moles of aluminum, but we don't want moles, right? We want grams. So we're going to do a just basic calculation, 2698 grams per mole of aluminum. The moles of aluminum cancel, the atoms cancel, and that will actually get us 2 grams. And if we do that, we end up with 4 times 2698 divided by Avogadro's number, which gives us 1.79 times 10 to the minus 22 grams. So this calculation, when you're doing the sort of these density problems, not too bad. It's essentially a basic calculation like we've done before, and we now have the grams part. So to get the centimeters cubed part, we do need to do a few little bit of conversions. So first off, unit-wise, this is the radius. So the length, right, equals, in this case, 2 times r square root of 2. And I personally want to eventually get to centimeters cubed. So what I'm going to do first is take my picometers and convert them to centimeters so that they're in the right units. So I'm going to just do a conversion to get my picometers into centimeters, because ultimately my volume wants to be in centimeters cubed. So picometers is, pico is 10 to the minus 12. So 10 to the minus 12 meters in a picometer. And in a meter, there's 100 centimeters. So this is just going to convert it into centimeters, because ultimately that is what we're looking for. So 143 times 10 to the minus 12 and times 100 gets us something like, we'll go with 1.43 times 10 to the minus 8 centimeters. And again, the purpose of why I did that is ultimately I want cubic centimeters. So now I could go into here and go 2 times 1.43 times 10 to the minus 8 centimeters times the square root of 2. And if I do that, I end up with something like 4.04 times 10 to the minus 8 centimeters. So again, just to make sure that I sort of get the right units and all that good stuff, that is why I did that. Now, this is not the volume though. This is just the length. So remember that we then need to convert our length into a volume. So the volume would equal the length cubed, which means I would take 4.04 times 10 to the minus 8 centimeters and cube it. That is going to give me the cubic centimeters that I need for my volume. So if I do that, I believe I end up with 6.62 times 10 to the minus 23 cubic centimeters. And that actually is the bottom part here, what I need. So at this point, I now figured out the grams. I also figured out the volume. So what is left to do is to take the grams and take the volume and basically divide it. So density is mass divided by volume. So in our particular case, the mass was 1.79 times 10 to the minus 22 grams, divided by the volume, which was 6.62 times 10 to the minus 23 cubic centimeters. And if we do all that fine calculation there, we will end up with 2.71 grams per cubic centimeter as the density of aluminum. So any questions on that calculation there? So when you're doing these, it's important to remember how many atoms each of those 3 cubic cells will have, because obviously that will allow you to get to the grams part correctly using Avogadro's number. And it's also important to know how it crystallizes because, again, it will give you the proper formula for the length so that you could get to the volume. Any questions on that calculation there? Okay. So why don't you try one here and see how you do? I think it was the same one we were just working on. All right, why don't you try this one here? Let me give you some info. There you go. So we want to look for the density in grams per cubic centimeter of RB. It crystallizes as BCC with a radius of 247.5 picometers. So take a few minutes here and see what you come up with, and then we'll talk about it. Okay, so let's take a look here and see. So this particular one here crystallizes in body-centered, which is important. Again, body-centered, as we talked about earlier, gives us 2 atoms and has a radius of 247.5. Also, because it's body-centered, to calculate the length of it, the edge length is a different formula. That is the 4 times r divided by the square root of 3. So again, we're looking for really our density in grams per cubic centimeter. So we're looking for both of those. So we'll start with the grams part, just like we did last time. We're going to go with it has 2 atoms. And again, using Avogadro's number here, we can go from atoms to moles. And using the periodic table, go from moles to grams. So sort of a basic calculation that we've done before. And it looks like if you do that there, you are going to get 2 divided by 6.022 to the 23 times 85.47 gives you 2.838. We'll call it 2.84 times 10 to the minus 22 grams. So again, this is the grams part that we need for the grams per cubic centimeter. So that is checked. Our cubic centimeter part, again, going to come from the length. And we do want to probably, again, do a conversion here just to get everybody in the right units. So 247.5 picometers. In 1 picometer, it is 10 to the minus 12 meters. And in a meter, there's 100 centimeters, right? And if we do that to 47.5 times 10 to the minus 12 and times 100 gets us 2.475 times 10 to the minus 8 centimeters. And again, here, we're really just doing this to get everybody in the right units for the end, so you don't have to do a conversion at the end. So we are now have our radius that we could put into our formula here. Get a fresh page here, I think. Actually, it did it for me, huh? Actually, let's go down here, I guess. So the length here is going to be 4 times 2.47. 5 times 10 to the minus 8 centimeters, and that is all going to be divided by the square root of 3. So we take 4 times our radius divided by the square root of 3. Gets us something like 5.716 times 10 to the minus 8 centimeters. We're then going to have to cube it to get to our volume. So if we do that and cube it to our volume, let's go to this page. So our volume will equal the length cubed, which gives us 5.716 times 10 to the minus 8 centimeters cubed. Gets us 1.87 times 10 to the minus 22 cubic centimeters. So that is, again, the second number that we really need to get to our density. So we're going to density mass over volume. So the mass that we had previously was 2.84 to the minus 22, I believe. So 2.84 times 10 to the minus 22 grams from the previous page, divided by our volume here. So we end up with, making sure you use your exponent buttons, obviously, 1.52 grams per cubic centimeter. Any questions on that calculation there? So these are similar, very similar calculations, or very common calculations that are done with these. Opposite of these are kind of a reverse calculation where perhaps they give you the density and then you can kind of work backwards and figure out something like how many atoms, how much, what the volume was or something like that, kind of going backwards, or the grams or something like that. All right, any questions on these? So in terms of these, really, you do need to know the three different types. So that's our simple cubic, our face-centered, and our body-centered. And you need to know how many atoms each of them have, basically. And in terms of the formulas for the lengths, I think it will probably be provided for you. So you just need to be able to use it correctly. But what won't be provided for you is how many atoms each one has. So you do need to know that. That body-centered, for example, has 2, the face-centered has 4, and the simple cubic has 1 atom. So those things you need to know. But the things like the 4r divided by the square root of 3 probably will be provided for you. Any questions on that? Okay. So I think for the most part, that should wrap this up, I think. That's good. They got the same number. We're not going to worry about closest packing. Not going to worry about that. So you don't have to worry about that. And here's just a picture of sort of an ionic crystal structure. Again, you can see that they do arrange themselves in a very ordered sort of pattern in sort of 3-dimensional space. And I think that should wrap this chapter. All right, any questions on this chapter here? All right, then we're off to the next one. So give me a second here to fix it here. Let's do that. Let's do that. Let's do that. Oops. And let's do. Let's do that. Do that. And. Okay. Let's see here. All right, so we're going to continue on to chapter 10 on your side. Does it look the right size? It's hard to tell on my side. I just want to make sure. Somebody just tell me if it looks good to you, screen-wise. It's not like super small, right? Okay. Okay, perfect. Thank you. All right, so in this chapter, we're going to talk about solutions. We're going to talk about colligative properties of solutions. There's some review material sort of in here in terms of concentrations and stuff like that. So we'll probably go over that a little bit quicker than normal and just kind of review some of those formulas that we actually saw in a previous chapter, a couple of chapters ago, I think. So let's talk about solutions. So when we talk about liquids and liquid sort of mixing, if they really do mix in each other, they're soluble in each other. And a lot of times when we talk about sort of liquids and solubility, we oftentimes won't use the word sort of soluble. We'll oftentimes use the word miscible. And if something's miscible, basically what it means is that it is soluble in each other. So when two solutions really do mix together, they're said to be miscible. And basically what that means is essentially it looks just like one solution. So it just looks like you have one solution in there, no layering or anything like that. Now, if we do get two liquids that are basically don't mix very well together, they're said to be immiscible. And that is where you do get those kind of layering that happens. So you'll see some distinct layering, for example, in the test tube. You can mix them, but for a little bit they may mix, but after a while they will sort of separate out into their own sort of layers. So for example, something that's miscible, if we take ethanol and water, they mix really well together and it will just look like one layer. And that's because ethanol essentially has
this OH group that works really well with something like water through hydrogen bonding. It's able to interact very well with each other. We take something like carbon tetrachloride and water, they don't work really well together because if you remember, if you just kind of quickly sketch carbon tetrachloride, it is a symmetrical geometry with everything attached the same. It is nonpolar. And when you try to put something that's nonpolar with something that is polar, like water, for example, water is going to try to use, as we talked about with its intermolecular forces, is going to try to use hydrogen bonding. Well, the best that the carbon tetrachloride could do is it's going to try to use dispersion forces, and they're not going to be able to, for the long period of time, interact really well with each other, and they're not going to be mixed or soluble in each other, and they basically will sort of separate out. So this brings up the idea of like dissolves like, and basically the idea there is things with similar sort of intermolecular forces are very soluble in each other. Things with different intermolecular forces, not so soluble. So when we talk about something that's like an ion and polar, it's all good. Take something that's polar and polar, it's good. Take something that's nonpolar and mix it with something that's nonpolar, it's good. It's only really when you kind of cross over trying to put the polar and nonpolar together, not so good. They're not going to mix really well or anything like that. And here's just an example. Again, you'll see some layering happening if you try to mix some solutions and they really don't mix together. Very similar to what you saw sort of in the halogen displacement experiment earlier on in the semester. So ionic dyes, again, are typically soluble in water, again, because water is polar. So they're able to interact really well through ion dipole, as we talked about. Remember, ion dipole is when you have basically an ion, say a positive ion, and a dipole, which is a polar molecule. It is that opposites attract, where they can interact with each other and work really well. That's essentially how solid ionic compounds like salt dissolves in water. As we talked about, they get surrounded by water, and basically it appears that they disappear, but they get basically mixed into the water network, and looks like they're no longer there. Now, there are things that we know do dissolve in water that are non-ionic, and things like sugar and ethanol. And basically, as I just mentioned a second ago, what they both really have in common is they both contain an OH group. And an OH group is a polar group. And because they do contain these, it allows them to interact again with water that also does pretty much the identical sort of deal through that hydrogen bonding. So that makes them very polar in it. Something like ethanol is not a very large molecule. So typically even guys where the part of it is nonpolar. So if you think about ethanol, you know, it's all these carbons and hydrogens on one end, and those guys are essentially nonpolar on this side. But because it does have this sort of one polar group, it makes it very sort of soluble and able to interact very well. The solubility of things like ethanol, where organic guys, where the carbons and hydrogen parts get longer and longer and it gets bigger and bigger, the solubility goes down a lot in water because of that, because at some point you have a side of the molecule that is just way too nonpolar and too big to interact very well, where it's trying to use just a small little section of it to do so. But usually very small guys, if you have like 6 carbons or less with that OH group, will be essentially pretty polar in water because it's not so big. Sugar, on the other hand, is a kind of big molecule, but the difference though, sugar, as we'll see a picture of it in just a second, is pretty much littered all over it with OH, kind of OH groups all over it. So everywhere there's an OH group, it gives something like sugar a place to interact with water. So since it has a lot of OH groups, it's very soluble in water. And here we go. So this is methanol. Again, methanol, sort of this part of it, kind of nonpolar, but it does contain, again, this OH group on it, which gives it a spot where it can interact with water through hydrogen bonding and be very small, soluble in it. Now, when we talk about something like oil and water doesn't mix, and really the major sort of component of oil is carbons attached to carbons, and those carbons have hydrogens attached to it. And carbon and hydrogen is non-polar. So oil is insoluble in water is probably a better way of putting that, insoluble. And the reason it's insoluble is, again, oil here is going to try to use dispersion forces as its main source of intermolecular forces because that's pretty much all it could kind of use. Water, again, is going to use hydrogen bonding. And again, for a short period of time, they could sort of mix because water could do a little dispersion forces. But eventually they will sort of separate out. And that's kind of like the oil and vinegar salad dressing. You know, again, you can mix it. It will stay together for a short period of time, but eventually it will sort of separate out from each other. And that's sort of the idea here. Also, you know, if you've ever seen an oil spill, the oil typically will float right on the water. It really won't mix with the water. And that's because oil, again, is very large molecules. So for something to dissolve in water, you basically got to break apart all the water-water interactions and replace them with very similar type of interactions. And for oil, you would have to put a giant hole in it, and it just doesn't sort of happen. And that brings up the idea of two terms that are sometimes used when we talk about sort of water and things sort of likeliness of water, or liking water or not liking water. And that is hydrophilic. And hydrophilic means that it does like water a lot. And that's polar parts of molecules. So for example, in our ethanol example, the part where it is all the carbons and the hydrogens is a nonpolar part, but again, that OH part would be your hydrophilic part of it that likes water. And that's different than hydrophobic, which is the part that doesn't like water. And that would actually be this part of it here. Our nonpolar part would be our hydrophobic part that doesn't really like water. Another example, which I think we talked about, I think the other day, was soap. Soap kind of has that similar sort of regions. Soap has a hydrophobic region, which is a nonpolar part. And that's the part that actually likes dirt and grabs the dirt. But it also has soap, a hydrophilic part that likes water, which again, as we talked about, the soap traps the dirt and then it's washed off with the water, because the water part of soap, or the part that likes water and soap, it will allow it to basically mix and wash away. And here's again that layering effect. If you take something like, this is sort of like oil and our water, and again, you can see there's really no crossing there. They do sort of separate out up on top. Over here is octane and carbon tetrachloride. These are two nonpolar solutions being mixed together, and you can see that they do mix really well together. They all look like one over here on the left. And again, that's because they are both, in that case, octane is nothing but carbons and hydrogens. So it's nonpolar, going to be using dispersion forces. Our carbon tetrachloride also using dispersion forces. So again, they're like dissolve like. So nonpolar and nonpolar going to mix. On the right-hand side, nonpolar and polar does not mix. So that brings us to the idea of solubility. And when we talk about solubility, when one substance like a solute dissolves in another, it's said to be soluble. So solid salt will dissolve in water. When one substance really doesn't dissolve in another, it's said to be insoluble. And there usually is a limit to the solubility of one substance in another, and solubility does depend on temperature. There are things that are usually always soluble in each other. Gases are always soluble in each other, and that's because gases are flying around. So just by the nature of gases, they are constantly mixing with each other and would be soluble in each other. Also, liquids are mutually soluble. So again, our polar and polar guys are going to be soluble in each other. Our nonpolar and nonpolar guys will be soluble in each other as well. Again, the ultimate reason why that is because they are using the same intermolecular forces that we talked about. Again, that dipole-dipole, hydrogen bonding, or dispersion forces. So again, guys with very similar intermolecular forces should be very soluble in each other. And ones that are able to interact really well with each other will tend to form some type of solution. And again, it's that idea of like dissolves like. Now, as I mentioned, there is sort of a solubility is dependent on temperature. So when we have a higher temperature, we usually will have a larger solubility of a solid in a liquid. And they sometimes tell you, right, if it's not dissolving, maybe heat it up a little bit. When you heat it up, you're adding some more energy. It's going to allow things to dissolve a little bit more. Everybody kind of to break apart a little bit easier and sort of mix. At lower temperatures, we have a larger solubility of a gas in a liquid. And that's because at lower temperatures, our gas molecules are moving slower, which means when it goes through a liquid part, it's going to be in that liquid part longer than at a higher temperature where it just kind of zoom right past, right, and not really stay within the liquid part. But because it's moving slower, it will stay in that liquid part longer. And the solubility of gases does depend on pressure. So at higher pressures, we have a larger solubility of gases, and that's related to like Boyle's law. At a high pressure, we have a very small volume, which means if we have a very small volume of gas, everybody's flying around in a very small area, which means they should be sort of constantly mixing with each other and be soluble in each other. And that's sort of what we see here, our interactions of our ion in water as it gets surrounded by the water. Again, our sodium ion here, which is positive, being surrounded by the negative side of water, which is the red circles, which is the oxygens here. Again, the oxygens being more negative in water. And that brings us a couple of ways that we can describe solutions. So a couple of different ways solutions are described is one is a saturated solution. And if you make a saturated solution, basically what that means is you have hit the maximum amount of solute that will dissolve in a solvent. So remember, a solution is made up of two things, the solute, which is the smaller part, and the solvent, which is the larger part. So if you've hit a saturated solution, you pretty much at that particular temperature, because it's based on temperature, you've hit the maximum amount of that solid that you could get to dissolve in that solvent. Which means if you continue to add more solid, it won't dissolve, it'll just start to pile up. So like, you know, you put some sugar packets in, it's going to dissolve, But if you take like the big giant thing of sugar and just keep dumping it into your water, your glass of water, at some point it's not going to dissolve anymore the sugar. It will just sort of pile up there on the bottom of your glass. And obviously at some point you've hit the saturation point to prevent it from further dissolving. Now, what happens when you don't get to that part where you're before that case, that is what is known as an unsaturated solution. And in an unsaturated solution, you haven't hit the maximum amount of solute that will dissolve, which means if you add more solid, it will continue to dissolve. And it will continue to dissolve until you've hit the saturation point, which is essentially a saturated solution. So it will continue to dissolve until, boom, you're at that point of saturation, and now you have a saturated solution. And then at that point, if you continue to add solid, no more will dissolve. So unsaturated, you could still get more solid to dissolve. Saturated, you're at the point where no more will dissolve. And there is a way to sort of go beyond that sometimes, and that's what's sometimes referred to as a supersaturated solution. And usually in a supersaturated solution, it's made by a couple of ways, but sometimes it is made by making a saturated solution where you've hit that point. And sometimes you'll even heat it up. And if you heat it up, you're going to do two things. You could also allow more solid to dissolve at the higher temperature, but you'll also be evaporating off some of the water. And typically what you do after you do that is you just let the solution sit, and it's going to cool back down. And once it cools back down from the higher temperature to the lower temperature, you now have a solution that has way too much solute dissolved in there, because remember, at the higher temperature, the solubility is larger than at the lower temperature. You could get less solid to dissolve. So as that temperature drops back down, you actually still have a solution at this point, but you have a solution that has way too much solute dissolved in it. It really shouldn't be a solution at this point because you have too much in there. And what you create is really an unstable solution at this point. So basically you have this really unstable solution. It's so unstable that if you just kind of tap the sides of the flask or the test tube, or if you just take one small, like that big, I'm going to circle it because you might not be able to see it, like that one small little piece of solid that you put in here to dissolve. And you just drop that one little measly crystal in here. That's enough to make the solution go, whoa, too much dissolved. And what will happen, it will go from a solution to a rock hard solid, as all the solid will come out of solution at that point. So in a supersaturated solution, typically you have way too much solute dissolved in that solvent for that particular temperature, and it creates a very unstable type of solution. And we'll skip that. And that's what's shown here. What we have here is actually a supersaturated solution of sodium acetate. And you can maybe pick it out, but you can see it's a solution here, again, made by making a saturated solution, heating it up to get a lot more solid dissolved, and then slowly letting it cool back down by itself. And now what we have here in the first picture is an unstable solution, basically in a supersaturated solution. You might not be able to see it, but I'll just kind of circle it right around here. They're just adding like one little drop of a crystal that was in there before. And as soon as they add it, you could kind of see it start to become solid and more solid form, and then it realizes I have too much dissolved, and all of the solid comes, and basically this entire solution now becomes a solid because all of the solid basically comes out of solution because it was way too much dissolved in it to begin with. So that's used to be a very common experiment people used to do at chemistry labs. They don't usually do it too much anymore because it resulted in a lot of broken test tubes and stuff, because people at this point go, how do I get that out of my test tube now? And people would break their test tubes, thermometers and stuff like that in it. So let's talk a little bit about pressure on solubility, the pressure of gases on the solubility of it. And external pressures can have an effect on the solubility of gases. And this is what's sometimes referred to as Henry's law. And Henry's law basically says that a solubility of a gas in a liquid portion is proportional to the pressure over the gas. This is also known as your soda can, basically, right? Again, in a soda can, you have water, you have some CO2, and before you pop the top of your can, it's under a very lot of pressure, which means the CO2, right, are all basically dissolved in the liquid part. Once you pop the top, the CO2 will now be released because for two reasons: pressure is less, and that CO2 molecules now have a place to escape right out the top. And that's the fizzing that you see right when you pop open like a soda can, for example. And what happens with a soda can, if you leave it long enough, is it goes flat. And that's because all the CO2 basically escaped out through the opening there, and your soda becomes very flat. And there is sort of a formula here that you could calculate. So C is concentration, K is Henry's law's constant, and that's different for different gases, and P is the pressure. So you can use this to figure out the pressure concentration relationship of a gas over a liquid. And let's take a look at this. So there's Henry's law's constants. Again, obviously would be provided for you if you needed it. And you can see, though, that they are different values depending on what gas you're talking about. Here's a much prettier picture of what I just drew, but same idea. Again, before you pop the top there on your soda can, a lot more of the CO2, as you can see, is dissolved here in the liquid part. Once you pop the top, a lot more of it can obviously escape out the top, and obviously will come out of solution under that less pressure. So here, if we look at it and we want to find the pressure of CO2 is required to keep the concentration of CO2 at 0.12 molar in soda at 25 degrees. We could use Henry's law to do that. So again, we have that. We would want to go to the table that we just saw, and this would be Henry's law's constant for CO2. Again, it's going to be different depending on the gas that you're choosing. And then we can use our formula. Here they use S in this formula. S is solubility, which is concentration. It's the same thing. C or S is sometimes used. And if we put this stuff in there, we will get, we're looking for the pressure. So the pressure is our concentration. So again, that's the same thing, which is 0.12. This is our constant that we got from our table. And we see that we need a pressure of about 3.5 atmospheres to keep our soda nice and, you know, fuzzy, if you will, and not so flat. Obviously, normal pressure is 1 atmosphere, right? And so that's basically 3 times the pressure that's in that can of soda to keep the CO2 level the right concentration to allow it obviously not to be flat when you open it and stuff like that. Hence why it's under very high pressures. Question on Henry's law here. Obviously the constants, like I said, would be provided for you if you needed them. All right, so we're gonna go through the next little part here kind of quickly because I believe we talked about all these already and kind of did these examples, but just some reminder of some concentration units. Again, this is our percent mass to mass, and that is our percent m/m, which remember is the mass of the solute over the mass of the solution times 100. Also, we had talked about percent volume to volume, right? And percent mass to volume. Those were percent units that we, I think, saw when we talked about molarity, molality in that chapter right around titrations, I think is when we talked about those guys there, if I'm not mistaken. So I believe we've done these, yes. So we'll skip these. We also talked about molality in an earlier chapter as well. And again, a reminder that molality not to be confused with molarity, which is capital M. This is lowercase m. And again, this is the molality is the moles of solute over kilogram of solvent. So again, those are important sort of guys that I think we've talked about previously. And so just a reminder here in terms of the molality, if we wanted to do this, we want to get the moles per kilogram of solvent. So we would want the molar mass here of our C3H7 OH and convert these guys into moles and divide it by our water, which is our solvent, which would be 0.175 kilograms. And we would divide it by the moles of that, which would be 60.09, so that is 61.7 divided by 60.09 gives us 1.027 moles divided by 0.175 gives us 5.86 molality. So remember, molality can be calculated by taking the moles divided by the kilograms of solvent. Right. Now, just to be clear, we did talk about percent mass, and molality. Yes, I want to make sure I'm not having like a wrong thought there or anything like that, right? Okay. All right. So then let's talk about mole fraction, which we definitely talked about as well. Again, the mole fraction is the moles of what you're interested in divided by the total number of moles. That one for sure I know we saw in gas laws when we talked about that. So some of these are going to be important, and there's again a reminder how to do the mole fraction. Again, moles of what you're interested in divided by the total number of moles. And Again, molarity, which hopefully you should know by now, which is our moles per liter. That one for sure we talked about. So using some of these sort of concentrations are going to help us understand some properties, which are known as colligative properties. And colligative properties are properties that depend on the number of particles that are dissolved in a solution, basically. So the greater the number of particles that are dissolved in that solution, the greater the effect it's going to have on things like boiling points, melting points. So when we have, for example, just the solvent by itself, say water molecules, say if you're going to boil it, for example, they're pretty much free to just, head to the surface and go through boiling. Now, when you start to put something in the water with it, say sodium chloride or something like that, or you dissolve something in it, glucose or something else dissolved in it. Now what you have is these guys that are in the way of water, right? So for water to get to the surface, it's got to kind of go around some of these guys, it's got to move around as there's these other particles in the way. And what ends up happening is, in terms of solutions, is once you start to dissolve some solute in there, some type of particles in that solution, it affects things like its boiling point or freezing point. So for example, the boiling point gets elevated. So instead of water boiling like it normally does at 100 degrees Celsius, it might boil at, say, 105 degrees Celsius. Also, instead of water, for example, if it was by itself freezing at 0 degrees Celsius, it will maybe freeze at -3 degrees Celsius, a much lower temperature. So the presence of these extra particles in the actual solution has a big effect on some properties of that solution in terms of how it may freeze, boil, the vapor pressure that we may see. So we're going to talk about sort of how these things are affected by these more particles that are in the solution. So the first thing that sort of gets affected is what's known as the vapor pressure, and the vapor pressure is lowered. So vapor pressure, if you remember, we talked a little bit about, but vapor pressure is the pressure of a gas over a liquid. So the pressure of a gas over a liquid will have an effect, will be affected by the number of particles that are there. And again, it's sort of a basic idea of what I was just drawing on the previous slide. With all those particles there, in order for those molecules to get into the gas phase, they kind of have to get around all these guys. They sort of interfere with those guys getting into the gas phase. And because of that, less molecules will go into the gas phase. And less molecules in the gas phase means you have less gas molecules above the liquid. Less gas molecules above the liquid means that you have a lower vapor pressure. So that's what it means by vapor pressure lowering. There's a formula over here, PZ equals x squared times px. And PZ is the vapor pressure of the component in the solution. This is the vapor pressure of the guy in the solution with the stuff floating around. This is the mole fraction. Again, that's what we talked about previously. And this guy here is our vapor pressure of just the pure substance by itself. So when we talk about vapor pressure lowering, it's defined as basically the pressure of the pure substance minus the pressure of the substance in the solution. So take a look at how one of these guys sort of affect. So here we have the vapor pressure of ethyl alcohol is 66.5 torr. Calculate the vapor pressure of ethyl alcohol in a solution of 0.2 moles of glucose when it's dissolved in 1.25 moles of the alcohol. So we could use our formula that we just saw. And basically, this is going to be the pressure of the alcohol times the mole fraction alcohol times the vapor pressure of the alcohol by itself is normal sort of vapor pressure. And the first thing we want to figure out is the mole fraction of the alcohol. So we see we have 1.25 moles of the alcohol. divided by the total moles, which in this case is 1.25 and 0.2. So that gives us 1.25 divided by 1.45 gives us a mole fraction for the alcohol of 0.862. And again, that's calculated exactly how we would calculate mole fraction previously. Now, putting this into our formula, we would take our mole fraction times the vapor pressure of ethyl alcohol by itself, which is 66.5. And what we see is we end up with a vapor pressure of this solution of 57.3. So just visually, sort of what's happening here is if we just had our ethyl alcohol by itself, you know, no problem. They're able to get to the surface, go into the gas phase, and you got all this gas above it. And that gas above it, when it's by itself, has a pressure of 66.5 torr. Now, when we take our ethyl alcohol and we put our glucose in it, again, these glucose molecules sort of get in the way. They kind of got to go around, if you will. And there's just going to be less gas molecules getting up here and escaping the solution. And it's going to result, as we can see here in this calculation, that the vapor pressure will drop to our 57.3 torr. So again, the presence of those extra particles in that solution is, in this case, really preventing that ethyl alcohol to get into the gas phase, causing less gas molecules. And again, we see a lowering of that vapor pressure, which again is the pressure of the gas above a liquid. Question on that calculation. Now, another important sort of thing that's affected is the freezing point of a solution. So the freezing point of a solution is affected in the same sort of way. It's actually lowered. So it's called freezing point depression, which means, again, here, the freezing point of the solvent by itself will be then lowered to a lower number once we start dissolving some particles in there. And again, it's the same idea that when you have, say, water by itself, all the water molecules, no problem, can come together and start to freeze. But once you sort of put, you know, something in there with it, like sodium chloride, right? Again, it's got all these other sort of guys in the way. It's preventing sort of those water molecules from just coming together. They also have to deal with kind of coming together with the sodium and the chloride in there. And, you know, it's going to cause it to has to freeze at a lower temperature and get rid of some more energy, basically, to do that. And there's a formula here for freezing point depression. It is the change in the freezing point temperature, which is that delta T, equals Kf times M. Kf is our freezing point constant. This is based on the solvent. So this is a value that you could go look up on a table. And the important part is when you look it up on the table, it is actually the solvent, not the name of the solution. So for example, if you had a sodium chloride solution, the solute is sodium chloride, the solvent here is water. So you would want to look up the value for water here in the table. M is our molality, which, as we've talked about and just saw, is the moles of solute divided by the kilograms of solvent. So when we do this, though, this is not the actual freezing point temperature, but this is the change in freezing point temperature. So to find that, we take the change in freezing point temperature is the temperature of the solvent minus the temperature of the solution. And that's an important one to remember because that will give you the correct sign on your answer. It may not make sense right now, but we'll see it here in a couple of examples and why that's important. Another thing that's affected is the boiling point. So the freezing point actually goes lower in a case like this. The boiling point actually gets elevated and it becomes higher. So the boiling point is actually raised in a situation like this. And we get pretty much the same sort of effect here. It's the same equation. It's our boiling point temperature. So this is the change in boiling point temperature times Kb, which again is the boiling point constant also for the solvent times the molality. Antifreeze or coolant that you put in your car actually does both things. It elevates the boiling point so your car doesn't overboil. Actually lowers the freezing point in case you live in a really cold area. Your car doesn't freeze all the fluids in it as well. So when you actually put antifreeze in your car, it actually does both things, raises and lowers, raises the boiling point, lowers the freezing point. And because this is freezing point elevation, the change in boiling point, or boiling point elevation, the change in boiling point temperature is different. Here we actually take the temperature of the solution minus the temperature of the solvent. So here we're taking solution minus the solvent, which is important so that you get the right sort of sign when it's all said and done. So here's a table, and these would obviously be provided to you if you needed it, but these are freezing point constants, these are boiling point constants, and these are the normal freezing point and boiling points that we have here. And remember, if you're not dealing with water, which is the normal 0 and 100 we're talking about, say you were using benzene, it would have obviously a different freezing point and a different boiling point as well. So you want to make sure, obviously, those two numbers you're using correctly. Don't always just use 0 and 100 if it's not water. A lot of times it will be water, but it doesn't always have to be. So let's see how a problem like this can work. So here we want to calculate the freezing point of a 1.7 molality solution, aqueous solution of ethylene glycol, which is antifreeze. And we can use our freezing point equation to do so. And if we use our freezing point equation, it is, again, the change in the freezing point temperature equals our Kf times M. In this particular case, they gave us M, which is here. We would want to go to that table and find the freezing point constant for water. And if you do, you will find on that table that it is 1.86 degrees Celsius per molality, which means we do have our Kf and we do have our M given to us in this particular problem. So to find the change in freezing point temperature, it is 1.7 times 1.86 degrees Celsius times M. The M's are going to cancel. And when you do that, you end up with 3.162 degrees Celsius, or 3.2 if you want to do a little bit of rounding, which might be good. We'll call that 3.2. Now, this number here is not the answer. This is the change in freezing point temperature. We're looking for what is the freezing point temperature. Now, because this is freezing point and it's depression, that is the one where we go, the change in the freezing point temperature is the temperature of the solvent minus the temperature of the solution. Now, the solvent here is water, and the normal freezing point of water is 0 degrees Celsius. So if we use that formula, the change in the freezing point temperature equals temperature of the solvent minus the temperature of the solution. We have 3.2 degrees Celsius equals this water usually freezes at 0 degrees Celsius minus the temperature of the solution. And if we rearrange this and solve for it, it tells us that the temperature of the solution is not 3.2 degrees Celsius, it's actually minus 3.2 degrees Celsius. And that would be the answer. So that's why this is important for the freezing point, and the one that we solve for the boiling point is correct, are important, because that will give you the right answer there in terms of the sign. You probably will get the right number if you do the calculation, but you might not get the right sign if you don't sort of rearrange that correctly. So basically what this is telling us is water by itself would freeze at 0 degrees Celsius. By adding basically our antifreeze there, it's going to actually go down to minus 3.2 degrees Celsius in this particular case for it to actually freeze. question on that calculation there? Okay, we will stop there today. We'll do a few more examples of this tomorrow. And today we are doing part 2 of our gas experiment. So we'll talk about that, obviously, and the calculations involved with that as well. So make sure that you do put here if you haven't done so already. And I'll see everybody in about 20 minutes.